everyone. My name is Ayushi Agarwal. I am Assistant Professor from Computer Science and Engineering Department of ABES Engineering College, Ghaziabad. Today in this video lecture, I will be discussing about non-deterministic finite automata, or in short form, we can call it as NFA or NDFA. So, in this video lecture, we'll be covering about what is NFA or NDFA, graphical representation for NFA, its formal definition, and some example questions based on NFA. In my previous video lecture, I have discussed about what is deterministic finite automata. So in that video, we found out that a deterministic finite automata is that kind of finite automata where there is a single path for moving by reading an input one at a time from current state to the next state, right? That is what we have concluded in the DFA video. So over here, now let's study what is NFA. I have previewed about the definition of DFA to you so that you can relate with the NFA and DFA. So the full form for NFA is non-deterministic finite automata. It can also be abbreviated as NDFA. So in NDFA, N stands for non, D stands for deterministic, and F and A is for finite automata. So finite automata are called NFA or NDFA when there exist many paths from specific input from the current state to the next state. Okay, so that means there is no single path. There are multiple paths possible for one particular input from current state to the next state. Every NFA is not DFA, but each NFA can be translated into DFA. So this statement means that any NFA can be converted to DFA. So the statement is true when we say that each NFA can be converted or translated to DFA, but a DFA cannot be converted to NFA. So if we talk about the exact finite automata, or you can say most prominent finite automata is DFA, if we compare among NFA and DFA. So NFA is defined in the same way as DFA, but with the following two exceptions. It contains multiple next states and it contains epsilon transaction. This symbol over here is read as epsilon. So epsilon basically means null transactions. Now, what is null transactions? Null transactions means you are not reading any input variable for moving from current state to the next state. So that particular transaction or that particular movement from one state to the another state is said to be as null transaction. We'll see more example on it, and then you will find out how the null transactions or epsilon transactions work. So over here, I have highlighted about the main characteristic difference between DFA and NFA. In DFA lecture, I have discussed that DFA does not accept any null move. That is, DFA cannot change a state without any input character, right? But over here for NFA, we state that it can take epsilon transaction. That means without reading any input character also, it can change state from one state to another. So that is why also we state that it contains multiple next states. Okay, so in let's see one example for graphical representation that will create more clarity about the characteristic difference between NFA and DFA. So this is the graphical representation for NFA. In the previous video lecture, I have talked about the main symbols or important symbols, how to denote various states in a finite automata diagrams. So over here, again, we can identify that which state is the initial state. Over here, Q1 state is the initial state. Why we are stating that Q1 is the initial state? Because it consists of an arrow, which is called as the empty arrow. Why we are calling it as an empty arrow? Because it is coming from nowhere. Okay, that is why we are stating that this arrow is an empty arrow and it is denoting a state. So that is why how we identify that this Q1 state is the start state or initial state. So this is the start state. And over here in the same diagram, our state Q3 is the final state because it has double circles or two circular structures entitled together. So this is our final state. And this our state S2, or sorry, Q2 is some intermediate state. So intermediate state can be of any number as per the requirement of our finite automata machine. So now let's see this graphical representation of NFA. So we found out that initial state will be the same representation, that is with some empty arrow. Any state is represented, that is always a start state or initial state. Any double circle state is always a final state, which is also similar to the DFA. Okay. Now see over here, by reading input A from state Q1, we are moving to two different states. One, we are moving to state Q2 and another we are moving to state Q3. So by reading same character or same input character, we are moving to two different states. However, in case of DFA, we have seen that by reading one specific input character, we are moving to one specific state, right? But over in NFA, we are reading one symbol and reading by one symbol, we are moving to different states. So that's the difference between NFA and DFA, and that is why we have stated that there are multiple states from one single input. Similarly, by reading character B from state Q1, it is again moving to two different states. One, it is having a self-proof of itself, and another, it is going to state Q3. Okay. Now, in case of DFA, if you remember, we have shown over here that it can have two states, A, B. But that is only in case of DFA. Over in case of NFA, we are not showing this, right? So, in case of NFA, why we are not showing both the symbols over here? Because our NFA can read epsilon transaction also or null symbol also. In case of DFA, we have, if we are mentioning any input variable, that should be transmitted from one state to the another state, or it should cover self loop. In case of NFA, it is not necessary that any state should read particular character input from moving from one state to another. So it is fine over here. So this is how the graphical representation or some kind of small working about NFA. Now let's talk about how we can write transition table for NFA. We can write transition table for NFA like this. Since we have inputs of A and B, so we will create the column for A and B. We have three states over here. First state is our state Q1, which is our initial state, then state Q2, then state Q3. Q3 is our final state, so we will put star over here. Now, taking the first state, that is our Q1 state, initial state, by reading A, it is going to two states. One is state Q2 and another state Q3. So we will mention both the states together over here in this column below input A with state Q1. So we will write like this, Q2, comma, Q3. Okay. Now, by reading B, it is going to Q1 and it is going to Q3. So by reading B, it is going to Q1 and it is going to state Q3. Now with Q2, from Q2, none of the symbol is read for moving from one state to another. So we will mention over here epsilon. If you remember, in case of DFA, we have mentioned phi, right? But over in case of NFA, we are mentioning epsilon. Okay, so in case of DFA, when we are mentioning phi, that shows that no transaction is from that state. Basically, that particular state is not reading any kind of symbol, right? But in case of NFA, if we are not reading any kind of symbol, we mention epsilon symbol over here, not phi symbol. Okay, now let's move on. With state Q3, by reading A, it is coming to state Q3, and by reading B, it is going nowhere. So we will keep epsilon. So that's the transition table for NF. That's the transition table for NF, or we can call it as NDF, right? This is our transition diagram. And this is our transition table. Now let's move on. So now by this, we can state a formal definition for NFA. NFA is a a formal definition for NFA can be stated as NFA is a non-deterministic finite automata, and it is a 5-tuple machine. It is similar tuple machine like DFA, but there is a small difference between how we write a transition function, right? So again, we are having the same symbols as we have in case of DFA. In case of DFA, we have Q, epsilon, Q naught, F, and delta. Similarly, over here also, we have the same symbols, Q, epsilon, Q naught, F, and delta. Over here, Q, it is similar like DFA. Capital Q represents a finite set of states. Epsilon, it represents a finite set of input symbols. Q naught states the initial state. F states the final state, and a transition function is delta. So in case of DFA, we have transition function as Q cross sigma gives Q. That means if we are reading or if we are moving from one state by reading some input symbol, let's say A or B or 0, 1 or any further input, we are moving to one state Q, right? By reading a set of Q, we are moving to one particular state from set of Q, right? But in case of NFA, what we are stating transition equation as Q cross sigma gives Q 2 to the power Q. So this states that there are multiple states for one single input, right? That is what we have seen the transition table in the previous slide. So let's see this transition function, how we can write the transition function for any NFA diagram. So let's see over here. We have stated the equation as Q cross sigma gives 2 to the power Q. This means that if we are stating the transition function for each state in case of NFA diagram or transition diagram, how we can write it as Q, first we have Q1. For Q1, it is reading input A. Okay, by reading input A, it is moving to states first Q2. Again, it is reading A and moving to state Q3. Together, this can be concluded as Q1 with the help of input A. It is moving to state Q2 and Q3. So that's the difference between how we write a transition function equation for NFA and DFA. Similarly, if we want to write for state Q3, since Q2 is not having any input or it is showing null transaction, so no need to write transition equation for it. Let's write for state Q3. For state Q3, it is having single input A and it is moving to state Q3 itself. So it is similar to DFA, but now let's see with Q1 with input B. For state Q1, over here it is B. With B, it is going to state Q1 first. Next, by reading from state Q1 having input B, it is moving to a new state that is Q3. Now together we can write and compile it as Q1 with the state input character B. It is moving to two states Q1 and Q3. So that is how we can write transition function for an NFA diagram structure. So that's a formal definition for NFA. Now let's study some questions based on NFA. So this is a transition table given over here. With the help of this transition table, what we need to do is we need to design an NFA. So see over here how we can identify which state is our start state and which state is our final state and which state is our intermediate states. So since over here, we have been provided with three states, Q0, Q1, and Q2. Over here, Q1 is represented with an arrow. So obviously, this is the start state. Our state Q2 is represented with star symbol. So obviously, this is the final state. And this Q1 is some intermediate state. Now, let's follow each row one by one and let's draw the NFA for this transition table. So first we have state Q2, Q0, which is our initial state. So obviously we will represent it with an empty arrow. Now from Q0, by reading input 0, we are moving to state Q0 and Q1. With input 0, moving to state Q0 and state Q1. Now, with reading 1, it is moving to state Q1. So we'll write it as like this. So this type of transaction can be seen only in case of our NFA, not in case of DFA, right? So in case of DFA, we do not write multiple inputs except for the final state. Other than that, none of the transaction will be shown with multiple inputs. But in case of NFA, any transaction can be shown with multiple inputs. That is the difference between in structure or diagrammatic difference between NFA and DFA, right? So what we have drawn, let me draw it again for you so it will be clear to all. So with 0 input, it's Q0. Again, with 0 input is going to state Q1. With input 1, it is moving to state Q1. So that's how we have drawn. Now come to the second row with state Q1. With state Q1, reading 0, moving to state Q2. Reading 0, moving to state Q2. Since the state Q2 is our final state, so we will have double circle around it to identify that this is our final state. From state Q1, by reading input 1, it is moving to state Q0. So that's how we can draw it like this. Now, from state Q2, by reading 0, it is coming back to state Q2. And by reading 1, it is moving to state Q1 and Q2. So this is a transition diagram for this transition table of NFA. Now let's define 5-tuple machine over here and try to write transition function for this transition diagram. So our 5-tuple machine consists of symbols what? Q, sigma, Q0, F, and epsilon. So let's define a 5-tuple machine according to this transition diagram. Over here, capital Q is Q0, Q1, and Q2. Sigma means input symbol. So over input symbols is 0, 1. Q0 is the start symbol. So over here, start symbol is Q0 itself. F represents the final state. So final state symbol is Q2. So this is how we can write all these tuples over here. Now let's write about delta. So delta function have equation as Q into sigma gives 2 to the power Q. So let's write transition function for each state transaction. Okay, so now let's write. So first of all, we have Q0 by reading input 0. Moving to state Q0 and Q1. Q0 by input 1. Moving to state Q1. Q1 with input 0. Moving to state Q2. Q1 with input 1. Moving to state Q0. Q2 with input 0. Moving to state Q2. Q2 with input 1, moving to states Q1 and Q2. So it's very simple to write. You just need to take the corresponding readings and you need to follow the correct format of writing and correct equation to represent. And that's how you can write a 5-tuple machine structure for any NFA. And you can draw a corresponding transition diagram if you've been provided with transition table, and vice versa also is possible. So this is one example or basic example with NFA. Now let's move on with the one example question. Now let's see this question. This question is stating that you need to draw an NFA with epsilon. Epsilon means input symbols. Over here, input symbols are 0 and 1. Accepts all strings with 0, 1. So over here, you need to draw an NFA that will accept the strings which will consist of inputs of 0 and 1 and have a combination of 0, 1. Now over here in this question, it is not stated that whether the starting of the string should be with 0, 1 or the string should end with 0, 1. So basically, we need not to worry about the start point. We need not to worry about the end point. We just need to have a combinations of 0 and 1 in our string. Okay, so basically, by reading such kind of questions, first we need to identify which should be the basic string that can be accepted with our NFA or with our transition table, diagram structure for according to the given statement, right? Now, let's say that our smallest possible string that could be accepted for an NFA structure according to this statement is 0, 1. Okay, now let's design an NFA that will accept our string 0, 1. Let's say that Q0 is our start state, having input 0, move to a new state, and having input 1, move to the final state. Okay, now this shows that we have an NFA structure for a smallest string possible according to this statement is 0, 1. And it is now accepted. From 0, you are being read from state Q0 and moving to a new state Q1. From Q1, you have input 1 and you move to the final state Q2. So this shows that smallest string is now accepted. But what about if we have next possible string as 0, 1 and 0, 1? Right? This can be the next possible string also. So what we can do is we just need to modify within this basic transition diagram that we have drawn as per our smallest string. So now 0 and 1 is now accepted. Now let's if we draw a loop over here with 0, 1, now this is possible transaction in case of DFA as well as in case of NFA. Now over here, we have drawn 0, 1 with the self loop. Now see, by reading 0, 1, it is accepted. By reading 0, 1, 0, 1, it is again accepted. Now any combinations of zeros and 1 are all strings now being accepted with this NFA. So that's the NFA for this particular question, NFA with epsilon 0, 1 that accepts the strings 0, 1. Okay, now let's draw a transition table for this NFA. We have input symbol 0 and we have input symbol 1. We have states Q0, we have state Q1, we have state Q2. Q2 is our final state, so we'll put star over it. Now, from state Q0 with reading 0, moving to state Q1. By reading 1, no movement, so we'll put epsilon. From Q1 by reading 0, no movement, so we'll put epsilon. From 1, moving to state Q2. By reading 0 from Q2, moving to state Q2. By 1, moving to state Q2. Okay. So that's the transition table for this particular NFA, right? So that is how you can design an NFA for any particular statement. First of all, try to identify the smallest string possible that particular statement for an NFA structure would accept, and then proceed it further, string by string. Obviously, it will start with the assumptions, but slowly and slowly, all the assumptions will be converted into the actual answer as per your given statement, right? So that is how you can work for an NFA over here. Now, if you want to check any other string further also, you can check for 0, 1, 0, 1, 0, 1. That is also accepted. If you want to check 0, 1, 0, 0, 1, that is also accepted. See over here how 0, 1, 0, 0, 1 is accepted. By reading 0, it will move here. So you read the element 0 from this particular string W1. Now read 1 over here. So you will read 1 over here. By reading 1, you will come to state Q2. Now complete the further string inputs 0, 0, and 1. So you will read 0. You will come back to state Q2. You will again read 0. You will come back to state Q2 and you will read 1 and you will come back to state Q2. Now Q2 is our final state. So you are coming back to the final state after reading all the inputs from your string. So that means that your string is accepted. Now, basic question comes to the student's mind that how you can identify that your string is accepted or not. So what you can do is start processing your string in the transition diagram. And if you end up to your final state, that means if you come back to the final state at the end by reading the last element of your string, so from that you can identify that your string is accepted by your transition diagram. So that is how you can identify it. Now let's move on and see one more example with NFA. So over here, the statement says that you need to draw a NFA with input symbol zeros and 1 and accept all strings of length 2. So that means you need to draw an NFA for input string 0, 1, where it will accept all those strings over 0, 1, but with the length of 2. Length of 2 means if we talk about strings with length 1, strings with length 1 over input 0, 1. So that obviously 0 and 1 only. So now strings with input, with length 2, it will be obviously 0, 0, 1, 1, 0, 1, and 1, 0, right? If we talk about strings with length of 3, so it's obviously 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on till 1, 1, 1, right? So that's the combination you must have read about. So over here in this transition diagram question, you are asked about to draw an NFA for this particular set of strings where length is 2 over the input 0, 1. Now let's draw this diagram and see how we can draw an NFA for this. Let's draw our starting state, that is Q0. You can name it another variables also. You can take it as QA or Q1 or Q2, any variable. So it is not specific that the initial state or starting state should always be Q0. Just for better understanding, I'm continuously taking Q0 as the starting state. Now moving further, you need to accept the string starting with 0 also and starting with 1 also. So let's say that if we have starting variable as 0 or starting variable as 1, moving to state Q1. Now, for starting symbol, we have justified. If we start with 0, we come to next state. If we start with 1, we come to the next state. Now, again, we will process the same scenario. The strings ending must be always, if we are talking about length 2, so obviously the strings must be ending with 0 or either it must be ending with 1. So again, we have only 2 scenarios. So either our string will be accepted with ending with 1 or the strings must be accepted that are ending with 0. So we'll say it like this. So see over here, our strings are 0, 0, 1, 1, 0, 1, and 1, 0. So over here, we identified that our strings must be starting with 0 or it must be starting with 1 as we have only input of 0 and 1. So these are the strings we have identified over here. So starting with 0 or starting with 1 must be changing the state from one state to another. So that we have shown over here. Again, we identified that now we have read our first bit string or first variable for every 2-bit string over here. Now, if we talk about 2-bit string, obviously only one more string is left or string variable is left. So next string variable must be 0 or 1. So again, we identified that next variable must be 0 or it must be 1 and that should be accepted. So again, we have mentioned 0, 1 on the transaction arrow over here, and that's how we came up to the final state. So this is our required NFA for this particular question, where you need to show the strings of length 2 must be accepted by your NFA for input symbol 0, 1. Right? Now, if you want to write the transition table for this particular NFA, you may write it like this. You have input zeros and you have input 1. You have 3 states again over here. Q0 is your starting state, Q1 is your intermediate state, Q2 is your final state. From Q0, by reading 0, you are moving to state Q1. From reading 1, you are moving to state Q1. From Q1, by reading 0, you are moving to state Q2. By reading 1, you are moving to state Q2. And from Q2, you are not reading any variable. So let's put epsilon over here. So that's a transition table for this particular NFA. Similarly, you can do more questions based on NFA. You may practice for NFA over input 0, 1 with length 3 or with length 4. You can even have input variables as, let's say, suppose you can have 2. This 0, 1, and 2, this is the input symbol, suppose, let's say, and you can have again the length of 2 variables, and similarly, you can practice many more questions on it. So that's all for this video lecture.